V formations to improve their efficiency. They also fly in something called Echelon formations, which may or may not improve their efficiency. That is what we're looking at in this podcast. So what is an Echelon formation? Well, it can be thought of as like a partial V, where either one length isn't as long as the other, or that it might just be one side to the formation. So for example, in figure 2, if we scroll up here, we see a formation with just one line of birds. And you do see this quite often in the sky. Like, it's actually quite rare to see a completely symmetrical V formation. Usually one side is longer than the other, or there's really only one side to it. So scrolling up to figure 2 here, we see here the birds are just in one line. So in today's podcast, we're looking at how flapping drones perform when they're put in this V formation and in this echelon formation. The flapping part might not seem like a big deal because we already know that when birds and our own airplanes fly in formation, efficiency increases. But the thing is that most of the studies that looked into formation flights only looked at fixed wing planes and not flapping. And we can see that in figure 1 here, we have the fixed wing kind of thing where these birds are kind of gliding. They're not really flapping. But then in figure 2, it's pretty obvious that they are flapping. At least the second one definitely is. Then the others probably are flapping as well. So some of the time birds do flap, some of the times they don't. And all the time they'll be in this formation when they do them. So as such, maybe these flight formations yield different benefits depending on whether you're flapping or not. And that might not seem like a very important point to us because our planes have fixed wings, but flapping is becoming more and more mainstream with many micro UAVs and even some smaller and medium UAVs starting to flap too. So one potential reason why we want to improve drones' efficiencies when flying in formation is so that they can travel greater distances, they can carry greater payloads, they can be smaller perhaps. So there are a lot of practical benefits to understand how flapping affects the efficiency of birds and drones when in V and echelon formations. So to look at how they're affected the efficiency, we're looking at this paper here called Studies on V Formation and Echelon Flight Utilizing Flapping Wing Drones. So this is open access and you can find the link below, and the DOI is at the end of the page here. So I'm looking forward to the research because they use a few different approaches. The first one is called unsteady vortex lattice, and then they go experimentally too, where they make flapping drones as well as buying them off the shelf and then testing to see how they perform in formations. So let's go through their unsteady vortex lattice method first because it gives some good flow viz in general and some good information. So in equations 1 to 6 down here, the authors used these to simulate just generally the flapping formations, just one way. They use other ways as well, we'll see later on, but this is one way. And these equations look quite intimidating, but they're actually not once you understand what they mean in a practical sense. So let's go through them quickly. So the first equation tells us the vertical induced velocity, so W, of something, so a point in space in the dx and dy position, based on the vortex that's far away. So if you have a vortex that's 1 meter, 2 meter, whatever distance away, what the vertical velocity of this particular flow will be because of this vortex inducing. So this is effectively the Biot-Savart law. The authors explain equation 3 to be the total induced drag of the entire V formation of birds. And then on the other hand, equation 4 tells us the induced drag of each bird individually. So equations 3 and 4 together are really powerful because they not only help us understand which locations of the formation are best, but then which ones are worst. So in practice, if there is a significant difference in efficiency between different locations, perhaps cycling birds or planes through them is best so that each individual gets the same overall benefits and you can fly as far, because if birds start dropping off, then the formation gets smaller, and that could potentially reduce the efficiency of all birds as well. So going together is probably a good idea. So equation 5 gives us the relative amount of induced drag of the V formation, and equation 6 is perhaps the most important equation because it tells us the best wingtip distance for birds in this formation. So the figure 3 shows an example of those 6 equations put into MATLAB and then calculated for various situations. So both plots tell us the drag on each bird for different flock sizes. So each line is for a different flock size for 2 birds, 3 birds, and 4 birds, and 5. The left plot is when the birds have no overlap between wingtips, while the right plot is when the birds have a 6.7 centimeter wingtip overlay. So for these plots, I'm not sure the exact span of the bird's wings, so I don't know the exact non-dimensional overlap we have here. Anyway, what both plots show us is that the more birds you have in the flock, the lower the average drag on each bird becomes. So this left plot here shows really only the leader and the tail birds, so the L and T numbers here, or letters here. They're getting pretty high drag still, but then the other birds between these two very much reap the benefits. They're getting like 20, 30, 40% reductions in drag. So it's kind of like going through a door. The first person has to open it, then while everyone else that goes through there really just requires a minimal amount of energy to keep the door open. You just hold open a little bit. Then the last person has to close the door and lock it. So the middle people are really the freeloaders. Now, another thing that these plots show is that at a 6.7 centimeter wingtip overlay, so the right plot, the drag of each bird and then the average flock is lower than when there was no overlay. So if you were to average these values on the right, they're a little bit lower than the ones on the left. That tells us clearly that even minor shifts of each bird relative to each other can greatly affect the drag force. And that seems really like a bit weird to me, because if there's a formation and then you have a side wind or even gusts that have length scales the same size or smaller than the formation, that will require each trailing bird or drone to move a little bit to get into optimal position, I would imagine. So that would be quite taxing. Anyway, just quickly, if you're interested in learning OpenFOAM, which is a top tier and free CFD software, check out our courses here. Now, let's get back to this paper. So the authors used something else apart from this apart from these equations, a software called Aero. And they call this is apparently an open source unsteady vortex lattice method solver. I recall only hearing it about maybe once or twice before, but I've never really used it. Anyway, if you're interested in using it, there's a link here for it. Apparently it's completely free and open source. The authors said this software has been validated with experimental data for a single ornithopter, and an ornithopter is a flapping aircraft. Anyway, the authors say that they'll test its accuracy for formation ornithopters in this research. So in figure 4, we see their geometry tested. The entire section is the wing planform for one bird/drone. It's colored with a surface pressure, which isn't too important for us right now. The wingspan is 70 centimeters, which is a pretty big drone, and even for a bird, that's pretty big. And then the flapping took a sinusoidal pattern with an amplitude of 15 degrees and a period of 0.5 seconds. So in other words, the wings flapped down to 15 degrees and then back up to 15 degrees, I guess, over 0.5 seconds. Then each bird was staggered half a meter behind the one upstream, and they were staged to the left or right of the upstream birds, 50 centimeters. So that, I guess, would mean that there's a 20 centimeter overlap in the wingtips, if I'm reading that correctly. That's a lot more than the 6.7 centimeter overlap we saw in figure 3, but I don't know what that wingspan was, so relatively speaking, I'm not too sure what it is. Anyway, the wings were at a 0-degree angle attack, and there was no side slip, so no crosswind either. They tested 1, 3, and 5 birds in formation. Figure 6, we see how the number of flapping cycles affected the RMS drag and lift. So let's zoom in a little bit here. Here we go. So we have how many flapping cycles in the x-axis affected the drag and lift in the y-axis. So a couple of things to note here is that first, the RMS value, the root mean squared value, was used here because during a flapping cycle, the amount of drag and lift on the wing will change. So by averaging it through RMSing it, you're getting one number to represent the entire cycle. The next thing to note is that there are two colored lines, row 1 in blue and row 2 in orange. The first row corresponds to the drag and lift on the lead bird. The second row is the drag and lift on each bird in the second row, and that is also the case for each bird in the third row, which we'll see later. So you can see that the drag isn't really affected too much by the number of flapping cycles. If you go 2 or more, you're pretty much getting the same result. The lift, though, if we scroll over a little bit, that's a little bit more sensitive to the flapping cycles. So even after 3 cycles, the 4th cycle is still giving a little bit of a difference here. So that's a little bit interesting to note. Anyway, in figure 8, we see the exact same thing, but now for the 3 rows of birds. So you have 5 birds, 1 leader bird, then 2 rows of 2 birds behind. And the exact same trend we see where the second row here is also plotted, but it's over the third row, so we can't really see the two. They're both together, they're so close. And that in itself is a little surprising to me because in figure 3, which used equations 1 to 6, if we scroll back here, it clearly showed that the first and last birds have much greater drag than the other birds in the formation. Figure 8, though, showed that the last bird, I guess, had the same kind of performance as the other birds behind the leader bird. So figure 8 is done with the Patera software, and I imagine that that software will be more accurate because it is validated to some extent. Anyway, these show that similarly the drag is pretty stable even after 2 flaps, while the lift changes a little still after 3 flaps. In table 1, we see how many flap cycles the author selected based on the number of birds simulated. For one bird, they went with just 2 flaps, and then for the 3 and 5 birds, they went with 3 cycles. So before we move on, let's consider whether that makes sense or not. So first of all, when there's just one bird, we need 2 flapping cycles to get a stable result. That means that the wake from the first flap needs to be shed downstream and effectively initialize the flow for then the second flap to perform correctly. Then when we have more birds here, we need more cycles. That makes sense because the wake from the upstream birds need to form, then hit the downstream birds to then yield the correct flow physics on the downstream birds. What's surprising to me is that you only need the same number of cycles for 3 birds as 5 birds, despite 5 birds meaning you have an extra row. So you have 3 rows instead of 2 rows. What that suggests is that each row is really only affected by the row upstream, at least in terms of the simulation stability. You only really need that first row to be stabilized, and then from there the next row is fine to go. So in figure 9 we see the flow viz of the unsteady vortex lattice method, and the results are pretty cool. You can see literally how the wakes of each bird flow into the bird downstream. The top left is for the single bird. Something a little odd to me is that the pressure on the upper surface seems to be completely positive for this top left figure. That means that downforce is created. Perhaps that's because this is a snapshot of the upstroke, I don't know. Anyway, as you move towards the wingtips, the wakes become more and more undulated. In the top right figure, we see the 3 bird formation, and one thing to note here is that I'm pretty sure that each bird is flapping in formation because each bird is in the exact same pose. In this pose, you can see how the wakes from the upstream bird, the wingtips flows, perfectly into the tips of the downstream birds. What's more, in this situation, I would expect more lift to be produced at the wingtips because you have all this upwash hitting the wing, so the effective angle of attack here should be greater. This solver can't predict separation as well, so the lift should be greater here as well. In reality, this upwash risks the tip stalling, and so perhaps the bird has to alter its wingtip angle or flapping motion to account for that. Now in the bottom plot, we see this similar wake formation, but for 5 birds in formation now. Table 2 gives the results, and it's a little surprising to me because the first is that when there are 3 and 5 birds, the downstream birds don't have higher lift coefficients. In fact, they're lower. As I said, the high effective angle of attack at the wingtips would make me think at least that a greater lift coefficient would occur here. But we're getting a reduction here, perhaps because the wake that washes over the wingtip onto the surface reduces the lift there. I mean, in the bottom plot of figure 9, we see some pressure changes around the wingtip, but it's a little hard to tell because the wakes are in the way. Also, from table 2, it seems like the induced drag coefficients actually increase for the trailing birds. This finding is very surprising as well. As the authors pointed out, there's also surprising because the birds weren't staggered in this best way. So perhaps in terms of formations, if done incorrectly, actually make things worse. Let's now move to the experimental results. So their experimental setup is seen in figure 10. The top 2 plots are their flapping mechanism. So on the top left and the top right, the wings go on these little latches here. Then the gears are connected to these latches through these linkages, and then they're driven by servo motors. The process makes the wings flap up and down. So in figure 12 on the right, we see their wing planforms down here on figure 12. And this is one side of it. So the lines that are going through the wings are carbon fiber rods for rigidity, and we can see them in figure 13 here. They're very thin. And it was a real arts and crafts session. So It looks like over the top they used aluminium foil, but it's actually mylar. Often plastic wrap is used for flapping wings, but I think they went with mylar here because it has a higher strength weight ratio. But then on top of that, I wonder why they didn't go with carbon fiber sheets instead. Anyway, they also got some commercial flapping drones as shown in figures 14 and 15, and I really like the realism of them. They have a colorway that matches an eagle, and the wing platforms are pretty similar, as we can see in figure 15, to figure 13. They both have a very straight leading edge, which I wonder why they're so straight, because a lot of birds have a slight bend at the midpoint, but others don't, so perhaps that's a topic for a future podcast episode. Anyway, one thing that may or may not be a factor is the feathers. So in birds, I'm not sure if every bird does this, but some definitely do, where on the downstroke, the feathers, each feather can clip together so that they form a very strong and rigid surface. But then on the upstroke, they unclip and the air can actually pass through them. And that helps the bird produce more lift, because when you think about it, you have a regular planned form when you're plunging down, then back up, you have these little gaps that the air can flow through. So less vertical force is produced on the upstroke, so the average lift is not zero. If you had these feathers just always clipped together, then going down you produce the same amount of same amount of vertical force as you go up, but in the opposite direction. So on average, it should be zero. So having the feathers being able to splay out and allow flow to go through them helps you produce more lift. Now in figures 16 and 17, we see how the birds flap, and it's pretty much what you'd expect. So let's not dwell on that anymore. Table 4, we see the different tests that they did. So down here in table 4, they range from one bird to several birds and with different phases and overlaps. The different phases refers to at what point in the flapping motion each bird is, and that's important because we need to reconsider figure 9 again, where if one bird is flapping down, and there are a lot of birds in the background in this podcast as well, so I guess it goes fittingly with this podcast. But in figure 9, we see that these wakes are really undulating. So the different flapping motions, the different phases, means that you might have a different wake hitting the wing. And that's something I think is important, is that the flow speed is important, because if the flow speed is lower, then the effect of a 180-degree out of phase motion will probably be different to if the flow speed were higher, because you're seeing different parts of the wake. So for example, if it takes 0.5 seconds for the wake to travel from the first bird to the second bird, and takes 0.5 seconds to flap, then being out of sync 180 degrees will mean that the second bird will see the wake from the first bird at 180 degrees out of phase. So the wake from the first bird, let's say, comes from a flapping down motion, the second bird will see that on the flapping up motion. Alternatively, if it takes 0.75 seconds for the wake to hit the second bird, then being out of phase 180 degrees means that the wake isn't seeing the wing won't see the exact same wake from the first bird when it was slower the flow. All that's to say that I don't think that the phase is so important, but rather the phase to flow speed, because that will determine what part of the wake the second bird will hit. Anyway, back to table 4. We see that they also did a battery drain test, which is literally a test of endurance. So that's really useful. That would tell us how long our battery will last, how long we can flap around and cruise for. Now on top of that, there are a lot of pictures which are nice to see, but not really important for us. So let's jump to the results section. More pictures here. Some pictures of the birds in formation. And let's go down to the results section now. Okay, so in figure 30, we see the average thrust for a single bird over the flapping phase, with and without a fan on. The fan off is the blue and the fan on is the orange. With the fan off, the thrust is much higher, and this could be for a number of reasons, including with the fan off, the wings have a better effective angle of attack. And I've said that term a few times, effective angle of attack. If you don't know what that is, then check out a video on a YouTube channel called Why the Effective Angle of Attack is So Important, Aero Fundamentals number 63. Either way, the fan off is way better here. And then from here, there is a lot of data to consider. Unfortunately, the authors didn't do a great job explaining the graphs, so it's very cryptic. Let's go through them and explain what they mean. So in figure 31, we see the average thrust produced by each bird in a 3-bird in 2-row formation. There is no fan on and there is no wingtip overlay. So each bird is exactly staggered from the other one. The x-axis is the position of the V formation and ranges from -1 to 1. So what this means is that in the sideways position, -1 means that that's the bird in the second row on one side. 0 is a leader bird, so the first row bird. Then 1 is the other bird in the second row. Again, the labeling is cryptic. I don't know why they didn't just label it like second row, left bird, middle, and second bird, right row, whatever. Anyway, what this shows is that in this particular V formation, the second bird rows produce over 20% more thrust on average than the leader bird. So this red and blue, these triangles are much higher than the green triangle. That means that these trailing birds can just slack off while flying, and the leader bird really is carrying them forward. So in figure 32, the left plot is the average thrust in a 3-row test. The x-axis is the time, but I think it should actually be the V formation. I think that's a typo. 4 different situations are plotted. The first is the blue, which is for no phase difference in flapping and no overlap. What this shows is that the first row and the second row birds produce more thrust now, while the third row bird produces less. The red line is now for no overlapping still, but now with a phase difference. Here the second row birds are still producing good thrust, about the same almost, but now the leader bird drops off. So if you wanted to play a joke on the leader bird, you could just flap out of sync and it would have to force that leader bird to flap harder. Now the yellow and purple lines give us some inconclusive results because the yellow is for the exact same conditions as the red, but now with a small overlay, and all birds now perform worse. But then the purple line is for a lot of overlap, and now all birds perform similarly. So there isn't really a general trend forming here. It seems like the best situation for all birds is the high overlap with phase difference flapping, but it's hard to predict how changing the bird formation will affect the results. Now in figure 32b, we see how long the battery lasted for the case of phase differencing flapping with a small overlap, and that corresponds to the yellow line in figure 32a. So the line is what you'd expect here. In the left plot, it shows that the second row birds produce more average thrust, so their batteries lasted longer here too because they don't have to work as hard, they're more efficient. And just quickly, on a different topic, we're giving away some free stickers. If you want some, then check them out here. Let's get back to the podcast. And let's skip to figure 33 now because I don't know what the legend is referring. Sorry, let's skip 33 because I don't know what this figure is referring to, this legend here. First of all, it's in inches while the authors say centimeters or millimeters. And I'm not sure what the y-axis value in the first part of the entry or the second part is, so I don't know how to read this graph. Anyway, moving on to figure 35, we now see the effects of the echelon formation on thrust. So surprisingly, for their results here, it shows that once you move past the 4th row, so this green triangle here, the bird 14, which is the blue triangle, this is the 5th row, the average thrust drops now. So in this case, it's not the case of more rows is better, but rather there is definitely a sweet spot, which is the 4th row. And all birds past the leader bird is producing more thrust, so the leader still has to have a harder time. And then the right plot is the battery drain test, and again, it's pretty expected because the more efficient you produce thrust, the longer the battery will last, and that's what we get here. It's very obvious what we're getting. One thing that's not obvious is that this line is pretty linearly plotted from the leader to the second row, whereas for the thrust, it's a bit more quadratic perhaps. Anyway, that's probably to do with power instead of thrust, I imagine. Anyway, in figure 38, we see some flow vis over a single flapping wing, and this is really important because, let's zoom in a bit here actually. Here we go. So this is the flow vis over a flapping wing, and this is very important because, let's scroll across, this is childproof it seems. Anyway, it shows the difference between how our typical wings produce lift and how flapping wings produce lift. So for our typical wings, the flow goes over them very smoothly and ideally, it should be uneventful. Here, that's not the case. So Let's focus on the top right row because it's clearer than the bottom row with all this stuff over the pictures. The leftmost picture is the start of the time sequence as the wing flaps down. So we get to the right, the vortex rolls up over the wing and produces more lift as you flap down. This vortex is a low pressure core, and that's how lift is produced. It then flows away downstream and the wing flaps back up and starts to cycle again. The fact that we do get major improvements in efficiency for flapping wings and for fixed wings as well is surprising to me because of how different the lift mechanism is between the two. For fixed wings, you have a very steady flow. For flapping wings, you have a very unsteady flow, but they both give very good improvements in efficiency when flying in formation, both the V and Echelon. And in this paper, we saw that even for minor changes in the formation, there's a very noticeable difference to the thrust production and efficiency. And that makes me think that perhaps there is more to formation flight than we know, because given how variable the flight conditions of birds are, for example, if you have gusts, it would be very tiring to constantly make adjustments. And also, like, let's say you have a different sized bird, so a younger bird or a bigger bird or whatever, that's going to affect where you have to stagger yourself. So perhaps there are other factors to consider in flight formation too. But still, we see that for echelon flights, there is still highly beneficial, and perhaps flying in an echelon is better because the middle birds get greater gains and only the front and rear birds get less gains. So the formation average efficiency perhaps increases on echelon flights compared to V formation. And with that, we come to this podcast. If you liked it, hit the me, likey, and subscribe buttons. And if you want to learn OpenFOAM, then check out our courses here. And if you want to get some free stickers, then you can see those on our website too. And if you're staying on YouTube, YouTube thinks you'll like this video, so check it out. Peace out, amigos.